Good afternoon, everyone. Welcome to our payment seminar series on Thursdays. And in the absence of Professor Jeff Raisler, I guess he asked me to take over to make the announcement for today's speaker, who is one of Professor Al-Qadi's PhD students, Ghazi Aurangzeb. And Ghazi has been working on asphalt mixtures and asphalt materials, all his, I know, PhD work here, especially his recent work on RAP materials, reclaimed asphalt pavement materials. He's going to talk about impact of high RAP content and volumetrics and performance properties of asphalt mixtures. So I guess without further ado, I will just get Ghazi going.
Thank you, Professor.
Thanks.
So, as Professor introduced the title of my topic, this presentation is based on the IST project R2737, which we just finished recently, and the advisor, Professor Imad Al-Qadi, is my advisor, as Professor Tutumala mentioned. So, before going into detail of the presentation, the outline of the presentation is that I will first give a brief introduction, followed by objectives of the study. Then I will talk about the mix design of the mixtures that we had, and then the performance test result, and then I will wrap my presentation up with finding and conclusion. So, just to give a brief introduction about RAP. RAP is reclaimed asphalt pavements. We generally acquire it by milling or ripping or crushing of the existing pavements in the field, and then they take it to the asphalt plants and keep them in stockpiles. In United States, the RAP content generally seldom exceeds 20 to 25% in the base base mixtures or the binder mixtures. And one of this is due to the few reasons. One of them is the introduction of high amount of fines and the variability in aggregate gradation, which is introduced by this RAP. Then the aged asphalt binder is also one of the key problem which brings RAP brings it into the mixtures. Due to the variability in aggregate gradation and fines, researchers have faced a lot of problems in achieving the required volumetrics for these mixtures. We have seen through the literature that people have emphasized on the performance properties of these mixtures, but somehow they have overlooked the challenges that volumetrics gave us in designing mixtures with high RAP. And due to these volumetrics and change in aggregate gradation, there is a potential impact on durability and stability of these mixtures with high RAP. So this brings us to the objectives of the study. The objective of the study was to quantify the feasibility of using high RAP content, by high I mean up to 50% in HMA. And for that, we needed to see that if we can actually design such high RAP mixtures with acceptable and consistent volumetrics or not. Also, we wanted to examine the impact of high RAP on the laboratory performances like durability and stability. We were also interested to see the effect of single and double bumping on these RAP mixtures. So the research approach that we adopted was that we made two control mixtures. Control means two mixtures made of virgin material, not including RAP. From two two sources, District 1 and District 5, we had two virgin aggregate sources and two RAP sources from District 1 and District 5. And the mixture that we made with those RAPs were three mixtures: 30% RAP, 40% RAP, and 50% RAP. The tests that we conducted were dynamic modulus test, fatigue test, moisture susceptibility test, rutting test, and the fracture test. So in total, we had 8 mix design made with the base binder PG6422. So in order to see the effect of binder bumping, we introduced two more binders, PG5822 and PG5828, as single and double bump binder, and made performance samples from all these three binders. So the material that we got, aggregate material, was obtained from Gallagher Asphalt Company for District 1, and for District 5 we got it from Open Road Paving. Most of the binders were obtained from MLC code, apart from PG5828, which we got from Asphalt Materials. All of them are part of, I think, Heritage Group. The red highlighted text shows the PG grade of the wrap binders which we did after extraction. These are the stockpile gradation. The two columns on the far right shows the extracted gradation of the wrap. We got wrap in two stockpiles, I mean in two gradation, plus 3 8-inch and minus 3 8-inch wrap. And 4.2 and 5.1 is the AC content of these wrap. This is for District 5. We have the same, we have some differences. For District 1 we have 4.2 and 5.1. For District 5 we have 3.9 and 5.5 asphalt content. So in this slide I am going to show how we wrap, how we process our wrap in our lab. First of all, as you can see, we got a wrap in two stockpiles, plus 3/8 and minus 3/8. We first dry our wrap for around 36 to 48 hours at 50 degrees centigrade. Then we fractionate the wrap similar to our virgin aggregate, and the resulting gradation that we get, we call it apparent gradation. This apparent gradation is what we use to blend the samples back and make the samples for GMM and extractions. And based on that GMM sample, GMM values, we found the effective specific gravities, and later on the bulk specific gravities of the wrap aggregate. One more important thing that we take care is that we sandwich our wrap between the virgin aggregates while we are heating it before mixing, so that we avoid the direct heating, avoid wrap from direct heating. So we came up with 8 mix designs that's shown here. All the mix designs were 19 millimeter or 3x4 inch nominal and maximum aggregate size binder mixes, and the end design was 90. Bailey estimation and Bailey theory for aggregate packing was used to come up with these mix designs. Bill Pine helped us a lot in order to come up with these mix designs. And these are the volumetrics for District 1's material. As you can see, the column 2, the second column shows the total AC content. We don't see much of significant difference in them. The third column shows the actual binder replace. If you are using, for example, 40% wrap, then the actual binder replace is 34.6%. The main column or the values that I want to highlight here are these VMA values. As I said earlier, that during the past studies, it has been we saw that there has been quite a lot of problems in achieving these such volumetrics. Some of them reported that there is a decrease in VMA with increase in wraps. Others reported there is an increase in VMA with increasing wrap. So here we proved that it's just a matter of effort you put into it, and you can get all the volumetrics good enough. I would say that fractionation helped a lot in giving us control over the gradation, and which helped us having a good control on these volumetrics. And it is the same reason that, let me explain this first. As I said earlier, we had quite a good control and gradation. This second column shows the design mix formula. This is the target that we want to achieve. The third column shows the extracted gradation. As you can see, the difference between them is quite negligible. The difference for 50% is a bit higher, but even then that is very, very good. For District 5 sample, district 5 RAB mixtures, these differences even went down. So I guess this is the reason that we were able to use the Bailey estimation sheets effectively. That whatever we are putting into it, this is actually there in the RAB. So to summarize the mixed design phase, the asphalt mixture with 30, 40, and 50% were designed using Bailey estimation sheet with good volumetrics and consistent. And the protocols that we followed helped us a lot to come up with these volumetrics and in controlling the gradation of these mixtures. The performance test results that we conducted were moisture susceptibility test. This is the part of the mixed design actually phase. So this is we follow the IDOT modified AASHTO allotment test, and in which we condition the samples for 24 hours at 60 degrees centigrade, followed by a 2 hours conditioning at 25 degrees centigrade, and then we do the IDT strength test. For district 1, you can see that as we increase the amount of FRAP, we can see increase in the tensile strength, and it is most probably due to the stiffened binder that is introduced by the RAP. And the TSR, the lower value for TSR, IDOT low values is 85, and almost and all of them clearly passed that limit as well. For district 5, okay, before that, district 1 samples were, the split TSR samples are also visually surveyed, and we saw this visual stripping that they almost behave similar to virgin aggregates, apart from the 50% RAP, which were 3 for one of the coarse particle size. For district 5 samples, we also see the same trend, the increase in the tensile strength with the increase in the RAP amount, apart from 40% RAP, which is slightly below than 85% threshold. We got all of the TSR clear. One important thing that I want to mention here, that this control mixture, district 5 control mixture, which Ibrahim is working on, is the typical district 5 mixture which is prone to moisture susceptibility, and it was clear here that it didn't cross the lower threshold of the tensile strength of 60 psi. So maybe including the RAP is also one of the remedies for this. Anyways, so the visual strippings for the district 5 samples were also very good, and all of them fall around or equal to the virgin aggregates, virgin mixtures. So tensile strength increased as the RAP content increased, and there was no influence by RAP on the TSR values, no negative influence, and the visual stripping rating is not affected by the RAP as well. So then we went ahead and did dynamic modulus test on all these mixtures. We had 8 mixtures. This is a experimental matrix for 4 mixtures only, I mean for district 1 only, and we compacted our samples to 7% air whites, gyratory, the uncut and uncoated samples. This is the master curve for district 1. We can see the effect of FRAP here, although it's not that significant, but you can as you can see, the blue line is the control one, followed by 30 and 40 and 50% RAP. So especially at this level, at higher temperature or reduced or lower frequencies, we can see some differences in the moduli. As I said earlier, that as we introduce RAP, it brings in some stiffness with it. So there is some indication of stiffness here. It's shows the effect of binder bumping here. As you can see, the blue line is the 30% RAP, the red line, followed by the green one and then the purple one. So it even reduces the dynamic moduli below the control. So it is quite, we can see that for 30% rep, this bumping was quite effective. For 40% rep, we do see a decrease as well, but still around the control mixture, but a bit higher than that. For 50%, we saw some good results as well. But in the end of the day, the District 1 E-star samples were so close to each other that it was difficult to differentiate them from each other. For District 5, we can see this is the effect of rep. It's 30, 40, and 50% rep with PG6422. PG6422 was the base binder, as I said earlier. So we can see increase in the moduli with increase. So in order to lessen the effect of this stiffness, again here we put PG5822 and 5828 in these mixtures. We can see a decrease in moduli for 30% rep. It's not that significant, but we do see improvement. For 40% rep, they almost behave same, almost all of them. For 50% rep, the single and double bumping did improve the moduli, but they almost remain the same. So in a nutshell, the complex moduli increase as the rep content increase, and the complex moduli decrease with the single and double bump binder grades. Although these effects were not always very consistent, but the general trend was there, and we could see it in the figures. The flow number were conducted on these samples at 58 degrees centigrade, and the failure criteria was 10,000 cycles or the 5% permanent strain. Flow number is a kind of indicator of rutting potential of mixtures. So as you can see, when the first set of bars, columns, that as we increase rep, we do see increase in the flow number, which clearly shows its resistance against the rutting. And it is consistent for all the binder types. I mean, for 30, 40, 50, we do see an increase in the flow number and showing increase in the rutting potential. Decrease in the rutting potential. We can also see the effect of binder bumping here, especially for 30%. It is most effective. As you can see, for single bump binder, we see a decrease in the flow number followed by the double bump binder, and it almost matched the control mix here. For 40% rep, we also see a decrease, and for 50% rep, we see decrease in the flow number as well. But as you can see, as we move up from 30 to 50% rep, the amount of virgin binder that we are adding to these mixtures is decreasing. That's why I guess this is one of the reasons that the effect of bumping is decreased on 50% rep. But this was not always very consistent. I mean, for example, here if you can see for District 5 material, we can see quite a good decrease in the flow number using the single bump and the double bump binder. The one important thing that I want to mention here is this control mixture. You will see also in the Hamburg wheel tracking results that this control mix, the District 5, which was prone to moisture susceptibility, behaved very weak in these tests, in the flow number as well as the Hamburg wheel tracking test. So Hamburg wheel was conducted at 50 degrees centigrade, number of passes were 20,000, and the failure criteria was 12.5 millimeter. This is for District 1 mixtures. We were expecting the same results as we saw in the flow number, and we got the same results, I mean similar results. And you can see there is a decrease in the rutting as we move from 0 to 30% rep, and then we do see an increase in the rut depths, but none of them reach to the control mix. So this is again, as I showed in the flow number test, the control for the District 5 was quite weak kind of in this rutting test, and it showed the same behavior in this Hamburg test as well. But one important, it failed the criteria here. This is a 12.5, but we are running it for 20,000 cycles. For IDOT, for PG6422, the failure criteria should be tested at 10,000 cycles. So for 10,000 cycles, this control mixture behaved well and it passed the minimum criteria of 0.5 inches. So we saw a decrease in the rutting when we increased the amount of wrap, and it was evident for both field tracking and flow number test. Rutting potential increased with single or double bump binder grade as well. But I would like to say that the rutting potential increased, but it didn't go up the control mixture. Then we did the beam fatigue test on it as well to measure the flexure resistance of these mixtures. 6 beams were tested, and the strain level that were used were from 300, 400, all the way up to 1,000 microstrains at a frequency of 10 hertz and 20 degrees centigrade. This is the typical fatigue curve. Where is, okay, we are missing something here. This is a typical fatigue curve that we obtained from these 6 tests that we conduct on these samples. And there was a relationship shown here, a simple relationship between the number of repetitions and strain. K1, K2 are the factors depend on composition and the properties of these HMA. K2 is basically the slope of this line. So higher the slope of this line, higher the value of K2, the absolute value of K2. If you can see, it's minus 3.4. Higher the absolute value of K2, better the fatigue properties of behavior of the mixture. So this shows the K2 values. As we can see, apart from 40% wrap, which there is a kind of a ditch there, we can see an increase in the K2 values with increase in the fatigue with increase in the wrap. As far as single bumping is concerned, we also see the improvement in K2 values when we go from the PG64 to PG5822, and this is consistent for both District 1 and, as I can show you, for one of the District 5 material. But when we introduce this double bumped into these mixtures, we always somehow saw a reduction in the K2 values. I may not be able to explain why this happened, but as the green ones, as you can see, all of them behave fatigue-wise behave less than the one with PG5822. But in a nutshell, all of these values were above 3.5 values, which was very important because this is the IDOT's lower limit of the lower threshold of these K2 values for their mixtures. So irrespective of how they behaved, all of them were above 3.5. Last but not the least, we did some fracture testing, and SAB test was adopted to determine the fracture energies of these mixtures. The sample thickness was 50 millimeter. Normally they use 25 millimeter samples, but since we had a 19 millimeter nominal maximum aggregate size, so we went for 50 millimeter, and the CMOD rate was 0.1 millimeter per minute. I'm showing the District 1 samples here at minus 12 degrees centigrade. We do see a decrease in the fracture energy as we move from 0 to 30% wrap, and it's quite significant difference here. And but as we move from 30 to 50%, we don't exactly see much of a difference. All of them behaved almost similar. The differences that we are seeing between 30, 40, 50% are within the experimental error of the test. And we do see also the effect of binder bumping. With single bumping, we have increase in the fracture energy. Also with double bumping, we saw increase in the fracture energy as well. Apart from this 50% 5822, the red one, all of them follow a good trend. For District 5 mixtures, this mixture, the control mixture, which was quite soft, at least I personally thought that it would behave better when it comes to the fracture energy, because it was quite soft in the rating and flow number, but it almost behaves similar to the mixtures with RAP. So we have a slight decrease in these mixtures as we move from 0 to 30% RAP, and then after that all of them remain the same, similar. 30, 40, 50 is practically, I mean, there is kind of a slight decline, but as I said earlier, it's within the experimental error. We do see a positive effect of single bumping and double bumping. It's not always consistent on every RAP type, but we do see, for example, for 40% we see a good effect of single bumping. For 30 and 50% we do see a good effect of double bumping. So in the end, the thermal cracking potential increased with the addition of 30% RAP, but above 30% RAP we didn't see any significant difference, and the single and double bumping improved the fracture energy and the low temperature fracture properties of the mixtures. I would now conclude my presentation. So achieving acceptable and consistent mixture volumetrics are possible if we work hard on it. So actually Berry estimation sheet helped us a lot, and the fractionation that we did also gave us a lot of control on it. And the asphalt mixtures that were prepared behaved almost equal to or better than the mixture apart from the cracking, low temperature cracking, in which we saw that single and double bumping is effective in gaining the fracture energy back. And in the end, I would like to acknowledge the Illinois Department of Transportation for sponsoring the project, Heritage Research Group, students and staff at Illinois Center of Transportation, and Jim Meister, who is always with us. He is including in the staff, but it's better to name him specifically because he always helps us a lot. And yeah, that's all that I had.
Questions for Razi?
Kazi, can you explain the visual stripping test a little bit? I'm not aware of how that thing is done.
Okay, when we do a TSR test, I mean tensile strength test, we split the samples between half because it's already split, and we rank them visually. We rank them visually by looking at their fine and coarse aggregates. I don't have a picture right now. That the amount of stripping, the amount of if an aggregate is clean, I mean doesn't have a binder coating, then it means it's stripped. So we have a criteria. If I go back to that, let me. So this is the criteria. If the amount of the stripped aggregate is less than 10%, then we rate it 1. And if it is between 10 to 25%, then we rate it 2. And if it is greater than 25%, we rate it 3. And it's a bit different for the coarse aggregate. So this is, as you can see, we can see kind of a stripping here. Here, you cannot call it stripping because it's just the breakage of the aggregate. We have these brown you can see here, these brown aggregates. So this is how we do it. Yes, sir.
Hey, it's a very good presentation, and it's interesting to see that the rep is going to be used as a remedy for moisture mitigation, and it's interesting to see that. But do you think that one conditioning cycle without freeze and thaw effect could have had any effect on the improved results for the moisture susceptibility test? Would you predict the same result if you had added maybe a couple of freeze and thaw cycles?
In my view, I would predict same results. I mean, of course, they will degrade, but because the material that we are getting is already coated with a binder, and then we are putting more version as a binder in it. So it's kind of a double coated. And one other theory that we can say that if a material which has spent around 10-15 years in the field and it has done well against moisture susceptibility, then it should do well in our lab as well. Irrespective of what is the conditioning, it may do better than the virgin aggregate.
I think, Ghazi, maybe it's worth it to make a comment regarding the PG5828 that we used.
Yeah.
It's true that we should be seeing, when we are using the 28, we should be seeing a better performance at the low temperature, which we did, but it was marginal. And the reason when we looked into the PG5828, it was actually 5827.
22.
20.
Yeah, the true grade was 27.
The true one, 27, which was closer. So it wasn't actually 28. So that's why the big difference that we were not we were expecting, we have not seen it. But it's interesting also to see that the flow was giving us very, very nice results when we run it. Okay, just a note.
Yeah. Guys, come on. Okay.